We all know what a linear model is, right? That's a progression thing. Go ahead. Ceci.
It's a line.
Yeah, true. It is a line. You did too.
Yes.
Yeah.
Wait, was that the person of us? That was the best. I got it.
Oh, it's a line, okay.
A line of best fit.
A line with best fit. Okay, what's the difference between the lines here and that one?
The distance to all the points is as low as you can make it.
What are the points we are referring to?
The data point.
The data points. Very good.
Good job.
Best fit is what you missed.
Oh, wow. That's funny.
I believe I showed a scatter plot last time for the example that we were doing.
Yeah.
Okay. Algebra, calculus, math in general, deals with functions, vectors, etc. Statistics deals with data. And in regression analysis, I've constantly made a point that matrices are quite important. And when I teach linear algebra, I'll keep on talking about it. The reason being, you can express a function easily. It's y equals f of x. You can express a function, a bivariate function, x comma y, f of x comma y, calculus 3 to take it, and easy. But what if you had more than 2 dimensions? This is a one-dimensional case in the sense, from a statistical standpoint, you have one predictor, which is x. Response is y. If I have y and x, things are easy. I can actually come up with a function that represents this data. That function has to be a line in this case because things are in a linear form. If you don't have data of this sort, perhaps you see a bunch of points U-shaped, then you won't be using a line. Rather, you should use a quadratic, a parabola. Okay. Multiple dimensions in a sense, not just one predictor. I have x1, x2, x3, x4, x5, x10, and x10. Everyone got
I got
that?
it. Yeah, extend.
Moving on. If you have a bunch of predictors, you cannot visualize. Not only that, you cannot fit a function and come up with a closed form. Writing a polynomial function is hard. Writing a polynomial in a surface defined by x and y, harder. And put x, y, z, 3 variables, good luck. 4, harder. So how do we extend it to multiple dimensions and why? In practice, we just don't have 2 variables related to each other. One of them being the independent variable. The example that we did last time, the one that I showed, sepal length, sepal width, we compared those 2. Great. But let's say we look at another example where we have the height of an individual. You can relate it to their weight. But is that the only variable that will determine a person's height? No. What are the other things?
determine someone's height,
gender,
genes,
genes. We would really like to, like that, yes.
Maybe
Three.
nationality.
Race, so
personality?
gender,
Oh,
ethnicity, race,
yeah.
the gene that is expressed, and these days you have more than just one gene, 10, 20, 30, 100 genes that express in certain ways. And in those cases, we need a matrix. Good. Okay, we'll get to that soon. A line of best fit is a line that best represents the data that we have, without getting into too much detail. What can we consider that a line of best fit? Reasonable. And how do we find this line of best fit? Was you, Jonathan?
Oh, it's based off the distance from all the points. I guess you do like distance formula maybe.
Very good. Not maybe, that is correct. Each of those epsilons. So that is what we call a residual. Residual is the actual value that you observe in the data minus the fitted value that you get from the model. What is the model? Well, the model is nothing but the function that you obtained. And we call it a linear model, y line. Yes. So the model for I equals 1 to n observations, that is the fitted model. Those two are fitted values. How do we get those fitted values? We get those fitted values using the data. So the I fitted value is given by that expression. The line of best fit overall is simply y hat equals beta naught hat plus beta 1 hat times x. Good. It becomes more important when you have more variables. When we get to general linear model, you will see. The goal is to take each of these residuals and come up with a line so that the sum of squares of all these residuals is minimized. So the smallest, the line with the smallest sum of squares of residuals would be the best line of fit. That should make sense. Did you follow the sentence?
Yeah.
So we have to square these Otherwise, sum of residuals will be 0. So if I move that line that way, do you think you would have the sum of squared residuals to be bigger than this case or less than the red line? Bigger.
Still bigger,
Smaller?
squared.
No.
Bigger, because the data is over there and your line of best fit is down here. What is it representing? The void, right? So it doesn't make any sense. So that is the line of best fit. Good. I can do this easily. One function, you'll get the answer. So can your calculator. But the calculator is limited in the sense it can only go up to linear regression, quadratic regression, exponential regression. That's it. Cannot do multivariate regressions, which will be the expansion. Key thing to note. Every time we did a test, non-parametric ones, estimately speaking, when we had Wilcox and Ransom, we had an expected mean. This is what I need to see if I have to side with the null. We did it with sign rank. We have it for classical Wallis. We didn't get into it because it's complicated. So same thing applies here. We have a theoretical model and we have what we get from done. Good. What is the theoretical model? It is written this way. What difference do you see?
So half.
There is no hat. What does putting a hat mean? It is an estimator. That is coming from the data. This is theoretically what we need to have. So there is one little additional term, which is epsilon I. Good so far? So what is epsilon I? Epsilon I is simply noise. Noise is what's going to cause variability. If you have a line, bunch of observations, should I use a different color? Good. Is there a variable? Is there a variable in the y values? For each value of x is y variable away from a line. Let me put it down. No, why not, Omar?
Because it's just going in a line.
It's just going in a line. It's a perfect line. There is no variation at all. That is not the case there. So come again.
There's more y's for each x on that one. So like x there. There's like-
It's one way, but that's not the only reason. Right? You could have the same x's, but this one can be up there, that down here. That is also. This is following a perfect line. And do you need statistics for this? No. How do we find that line?
Connect the dots.
Did you just say connect the dots?
Yeah, look, if you connect the dots, it's gonna be a straight line.
Oh, he's got.
So we find the slope, we find the y-intercept. Easy to do it here because it forms a perfect line. Not the case over there, which is why we need the process of regression to get us that line. Okay. So this term, noise, is what's going to push those numbers back and forth. That is variability. So noise, variance, one and the same. We have a condition being those values must have a normal distribution, mean zero, some variance, sigma squared. If it is not normal, then noise probably is getting added more on this side, less on that side. That is not going to give you a good estimate. So is it possible to know the exact value of epsilon I? Clear? Or not?
It's just small. Doesn't really matter, it's very small.
But we need to know that noise are going to fit that model.
So we didn't make the model yet.
Can I get the exact value of beta naught? There is a word up there, very important word, starts with the letter T.
Theoretical.
Theoretical.
Empty.
So in terms of theory, this is what we have. But if it's theoretical, we don't know what that value is. We found beta naught hat using the data, beta 1 hat using the data. So the residual that I found here, original data, hence actual value, minus the fitted value, the value that you get from the data.
So the actual is theory.
That is correct. Theory in the sense that's what the data has. Good, so far. So once we find beta naught hat, beta 1 hat, we can check for those assumptions. Here is a case, can I erase this?
Yeah.
That's sort of ideal. If you look at the epsilon i's, it actually wasn't skewed in one direction, right? Some here, some there, some here, some there.
That can't work.
Oh, God.
I think you missed a point.
I messed up here.
What information?
Right, so what is happening over here?
Dots AF.
It's skewed.
Too much, too close,
Yeah, too much.
right? If I fit a line over here, the epsilons are close. Yes. Too much variability here, too close over there. So you don't have a case where epsilons are normally distributed. We can verify that using the data. Good. So after you fit a model, you get the epsilons to make sure that things are normally distributed.
So if it's not, then we can't use this, right?
Then you don't have an
Can you
appropriate
repeat
model.
that?
Come again?
Can you repeat that?
So epsilons here clustered together. Low values of epsilon there. So you've got large values of epsilon estimated, too many small values, significant variation, there is a skew.
Okay.
If it is a proper model, then the number of epsilons that you estimated on this side and that side would be more or less the same in terms of distance you will have among them. Not an exact one, approximate one.
Got it,
And it will satisfy that condition. Good,
got it.
important condition. And y is dependent on x, they go in pairs. So that said, we started a problem in R. We did a scatter plot. We did not put the light on it. Good. We can switch to R now.